everyone. My name is Salah Daddinounou. I started my PhD in TMA last October. The topic is test and reliability of spiking neural networks. For now, I started by testing the magnetic memory, and I recently moved to spiking neural networks. So I will just be in my presentation. I will be focusing on the design. I found it important maybe to start by placing things in context. Where all started in the early 40s when people were interested in intelligent machines. The first inspiration were from biological neural networks or the brain. So from there, some first generation of neural networks were proposed as like the Perceptron, and then the second generation is the what's called now the artificial neural networks, the majority of them, and the third, which interests me, is the spiking neural networks. I will give some the motivations behind this kind of network, and of course talk about the differences between these generations. The motivations, I can already say that the big two advantages are for neuroscientists research and for machine learning, and finally the good way to implement these spiking neural networks in order to fit or to benefit from the all its benefits is to look for beyond von Neumann architecture and use special and dedicated hardware for these spiking neural networks. As small reminder, where all started, in the brain we have neurons and synapses. A neuron has dendrites where information comes from, and the axon in order to transfer the information to the next neuron. The important thing between the two neurons, there is what we call synapse, which is important, which is responsible of how much the connection between the two neurons is important. So basically the information is, or learning is made by, learning can be seen by how much the two neurons are connected via the synapse. And the synapse is this small gap where neurotransmitters can move through the two neurons. So the first generation was simple Perceptron, which is a simple logical unit, which receives and integrates the arriving signals from the surrounding neurons. It sums the signal, the weighted signals, and if it reaches a certain threshold, it fires and it gives the signal to the next neurons. Otherwise, there is no signal. The importance. So what we are gonna be looking between these different generations is how the information is encoded and how learning is done. And for this one, Hebbian learning in very catchy phrasing is when the neurons that fire together wire together. As we said, that's just like what happens in a real nervous system. There is no notion of time, which which makes it very far from the real biological systems. The second ones we have in the second generation, we have introduced the activation function, which is more smoother than a step like the previous generation. And we have introduced more functionalities, like the way learning is done is by back propagation, basically looking at the label at the output and comparing it with what is given by the neuron, getting the loss function and minimizing it in order to adjust the weights in order to give a better better response, which is close to the label that we want. And for these generations, we notice that this is a supervised learning, meaning that we always have to know what to give or to feed the network with the desired output before getting it learned. So it has been 3 decades almost since the birth of these spiking neural networks, and the dynamic of this spiking neural network is a bit different. We have the what we call the action potential in the potential of the membrane is important. So we derivative of the, so V is the potential of the membrane, and C is the capacitor of the membrane of the neuron. So basically it says that the dynamics is dependent on the arriving currents and external currents, and this is important only for the input neurons, where an external signal can be injected. And then we have the other subsets of neurons. We have the sum of weighted signals coming from the other neurons, and we introduce another term in order to make it more biologically plausible. This is a leaking term, and we are gonna talk more in detail about what makes this spiking neural networks more close to the brain. So in this, we have always neuron receiving pulses. Those are like spikes, and when it reaches the neuron, reaches a threshold, it fires, and there is a certain period where there is no activity of the neuron, which is called refractory period. And so in this figure, we can see several functionalities and characteristics of biological neurons, which are being mapped to spiking neural networks. First, you can see this is an external A is an external input, which can be like this is for the input neurons only, the first layer. We can see that when the input is not enough to make the potential of the membrane reach the threshold, there is leaking and there is no firing. This is there is no firing, but there is no postsynaptic signal. And then if we have a stronger or a more consistent input signal, we reach the threshold, and the response, there is always a certain firing, and as I said, there is always a refractory period between the signals. So in this time, there is an stimuli, but the neuron doesn't respond during all 20 milliseconds or so. And then we can see for the more hidden neurons in this in the right hand side, um, so the stimuli for these neurons are not continuous signals, but they're spikes because they are coming from other neurons. And you can see the same thing. We have always um, accumulation. So the potential of the membrane is accumulating the arriving signals, and between the spikes there is leaking. If it reaches the threshold, it spikes, and etc. Now that the model is presented, if we want to map these functionalities into our new spiking neural networks, we have to understand some important characteristics. As I said, that we have to have accumulation. If we want to have a close to spike network which is close to what the brain does, we have to have something, a neuron that accumulates spikes, which has also a leaking over time, which fires, so the response is only like spikes, and it has to have a refractory period between these spikes in which there is no response. Lateral inhibition, this is between neurons. Lateral inhibition for neurons in the same layer. When a neuron fires, it has to set the other neurons at zero. Because it's like competition, and homeostasis is a way to dynamically change the threshold, and this is something not important in our presentation today. And if we want to map synapse, we have to have variable conductance, so between the two neurons, which can be presented as potentiation and depression, as we will talk about here. So now all the learning rules should be in the way the synapses are in the dynamic of the synapses. So we see here, we call it the spike timing independent plasticity, which way to adjust the connection between the neurons. We have an input. If the neuron spikes just immediately after, this means that there is a big connection between the two neurons, and we have potentiation. The weight between the two neurons is increased, and if we have to wait a long period of time, there is an increase in the weight, but because it's smaller. On the other side, if the postsynaptic neuron fires before the presynaptic neuron, that means that the signal which made this postsynaptic neuron is not coming from, for example, pre1. So what we should do is to decrease the weight here and increase it here. And that's what we call depression. Now, how we encode information into this network, as we said, it has to be all the inputs has to be spikes. So we have to, if we want, for example, to inject if the task is recognition of digital recognition, we have to model each so each pixel in the picture is an input has to be fed in an input neuron, and the way this is done by translating the intensity of the pixel into spikes into a Poisson-like spike train, and the firing rate has to be proportional to the intensity of the pixel. And of course, afterwards, as all the learning is done using a CDP, and the output neurons are by feeding multiple trainings, we start to see classes in the output without presenting any labels, and that's why it's called supervised learning. Why SNNs? The motivations are in the first place relates to energy consumption. The brain is very energy efficient with almost 20 watts as compared to the state-of-the-art INNs, which are 10 times more, they consume 10 times more. The brain is has a high connectivity with 100, estimated 100 billion neurons and 1 quadrillion synapses. This makes it very complex, which brings me to the next point. This complexity is not well understood in neuroscience. So having this kind of networks may help to advance research also in neuroscience. Well, now the implementation. If we want such networks to perform well and use as low energy as we want, we have to find another way than the digital CMOS. There are multiple propositions for that, but the common thing is, as I presented, any neuron has to implement the different characteristics that we said. For the synapse, we use emerging non-volatile memories in order to have something which is tunable. At the same time, which can be saved with when there is no power. So the network is presented like in crossbar. I will talk more about how the synapse is done. We use what we call the spin transfer torque magnetic tunnel junctions, which is non-volatile memories having 2 states. But when combining multiple of them together, we can create multiple conductance device. We can see how the resolution of the conductance can be enhanced by using multiple in parallel or even in series MTJs. And you can see, for example, for the extreme for 36 MTJs, we can get something very resoluted in conductances, and that's what we want, and that's what we are playing when we are using STDP. We are playing on the conductance of the MTJ, of the synapse, sorry, which makes the connection between the 2 neurons more or less important. I think I have 1 or 2 minutes to present the avenue of research that I'm gonna be looking is fault modeling of all that and testing. So basically, in the team, they have already done some works on that. This is an inventory of all the faults that can be found in such networks. We can talk about the dead synapse, like all the MTJs. Basically, this is as I said, an extreme way of presenting it. Basically, we can use between 4 and 6 MTJs only. So we can get, the dead synapse can be found by when, for example, all the MTJs or the memories are there is breakdown or something. Degraded plasticity when some of them have a permanent default. Synapse can be stuck at one value in a way that don't make the synapse tunable. And for the neuron faults, we can have a dead neuron if one of the components that I presented earlier is not working. Deadly synapse activation, because actually I didn't go into details in how these neurons, it sends a lot of signals when it spikes, which control at the same time the surrounding neurons and the ways to which it's connected. We can have delayed spike faults, like if you and this is parametric fault, where it takes some time or it anticipates, so it doesn't spike at the good moments, or lateral inhibition between the two the neurons when it spikes. If it doesn't reset the competing neurons at the good moments, this may be a good fault. Or stack at lateral inhibition. So this is also another fault which can occur here. I think I gave an overview of this network. So I presented the generations of the SNNs, and we are interested in the third spike in third generation spike in our networks, and its neuromorphic implementation. The learning rule is back timing dependent plasticity as opposed to backpropagation for the SNNs. Hardware implementation, there are some different emerging non-volatile memories. I talked about only magnetic time junction, but we have phase change memories and memory source. And finally, fault modeling, which will be the points that I'm gonna be looking for in the future. Thank you.